welcome to Chapter 10. Chapter 10 is all going to be about circles. And before we can start talking about circles, we have to make sure that we are all understanding the same language as far as the parts of a circle and things like that. Most of this is going to be pretty familiar to most of you, but we're just going to go over it again just to be sure. And there are a couple things that might be new. A radius of a circle. A radius is simply a segment, and you can see in the picture there that goes from the center of the circle to the edge of the circle. The diameter is twice as much as the radius. It goes through the center of the circle. It's twice the length of a radius. Do not mix those two up. Both those are segments. Something that might be new to you is the idea of a secant. A secant is a line that intersects a circle at 2 points. So that's something different. A chord is a segment that has endpoints on the circle. Now, the difference between a chord and a secant is simply the chord is a segment with endpoints on the circle, and a secant is a line that contains a chord but goes beyond the circle. So that's an important difference. A tangent is a line in the plane that intersects a circle at exactly 1 point. That point is called the point of tangency. So, a couple things to keep in mind, and this does kind of show up in the assignment, so maybe worth looking at, is that some things are segments, okay? And those are radius, diameter, and a chord have to be a segment, have to be segments. They have to have distinct endpoints, okay? The radius endpoints are at the center and on the circle. The diameter endpoints are both on the circle, but it goes through the center. The chord endpoints are both on the circle. Diameter is technically a type of a chord, is the longest chord of the circle, but that's the diameter. Finally, we have if those are segments, then we have lines. Lines are a secant and a tangent. Now, we can have a tangent segment as well. So that can happen if it's part of a tangent line. So a segment can be a tangent if it's part of a tangent line, but technically a tangent is a line. So those are some very basic parts. And part of what we're going to do is simply identifying what's what. What is AC? So if I look at AC here, and I notice that AC has has 2 endpoints, so it's a segment. One endpoint on the circle, 1 point at the center. Clearly that's a radius. If I look at AB, much more interesting, AB, now we have both endpoints that are on the circle and going through the center. That must be a diameter. Ray DE. Now, we haven't talked about things being a ray, but a ray is part of a line, so that's okay. Ray DE right here. Okay, so going that direction. Nice that it straightened out for me. That's a tangent. That's a tangent because it touches a circle at 1 point. And finally, line AE right there, that whole line, that is a secant. So again, just being able to identify those points, knowing the different names. The word secant is probably new to you, but not too tough. Not too tough. And the reason secant is important, by the way, it will come up later in the chapter where we're going to talk about secant lines and how they intersect. So that is something we are going to see in the future. Again, just identifying parts, a little more practice with this. So if I look at AG here, just A to G, that is a segment. It has both points on the circle, and it does not go through the center, so that is a chord. And again, if I look at, say, CB here, CB right there, that's going to be a radius. We could name a tangent and a tangent segment in this picture. So a tangent line, we would probably say, I could say dB, DE, ED, EB, anything like that with a line symbol. Remember, if we're naming a line, we use a line symbol. So if we did that, say DE, that's how we name the tangent line. A tangent segment, again, making sure, this is going right back to chapter 1, isn't it? Using the correct symbols. So naming a tangent segment would be the same thing, DE, but with the segment symbol. So just watching those symbols again, it's going to make a difference. So be aware of what's what. All right, when we have two circles in the same plane, those two circles can be tangent, which means that they just touch each other. They can be intersecting. In fact, we can see this pretty clearly in the three different diagrams that we have here. Our first diagram here is a picture of intersecting circles where they have 2 points of intersection. Another thing we can have is two circles that are tangent. Now, they can be tangent internally or externally. Internally means one is inside the other one and they just share a common point that way. That's the one on the left. The one on the right is a common external tangent for circles. And the third choice is they could either not intersect and be completely separate or be what we call concentric circles. Concentric is a word we're going to see now and then. Concentric means that they have the same center point. They're different radius, but they have the same center point. So that's a lot of different situations we can run into with circles. Nothing that should be very surprising to anyone. When I have two circles, one thing that we can often have is what's called a common tangent line. Now, a common tangent is simply a line that is tangent to both circles. So, and of course, we're going to do our best to estimate these, but there's always a little tricky drawing them. That would be a common tangent for these two circles, but there'd be a second one here. Those would be considered external tangents. We can also have what's called common internal tangents. Common internal tangents are going to like zip through the center here, like that. And there'll be another one that's going to zip through the center here like that. So these two circles could have up to 4 common tangent lines. Now, that's because the two circles are separate. If the two circles are touching, like they're tangent circles like this, then I could have 3 common tangent lines. You're saying 3? How do we get 3? I've got these two, but where's the third one? Well, the third one actually cuts through the middle because they're tangent circles. They're only touching at a single point. We can sneak a line right in there, right through that point of tangency that has to exist between these two circles. There has to be that point of tangency right there. And so I can have a third common tangent line. If the two circles are intersecting, other than being tangent, if they're clearly intersecting lines, then, sorry, I want to get back to my line tool, then I'm only going to have the 2 external common tangents, one there and one approximately there. I didn't draw those as well as some of the other ones, but actually the fact that I drew the other ones as well as I did is rather surprising because these are tricky to draw. So we can have common tangent lines that way as well. All right. A couple very interesting theorems that we're going to deal with because now we've learned the parts of a circle. Of course, we're going to start learning some theorems and applying some algebra to that. This one is pretty important. If I have a radius of a circle and a tangent line that is tangent where the radius at point P there, so the point of tangency here is point P, and QP is the radius, then those two must form a right angle. Okay, so those are perpendicular lines. So a radius and a tangent are perpendicular at the point of tangency. And if they are perpendicular like that, then that's a tangent line. That's going to become very important to us in just a minute, that that's a right angle. Because what happens when we get right angles? When we get right angles, we get right triangles. And we're going to start looking at some right triangles, which should surprise absolutely no one because we just got done with a whole chapter on right triangles, so why would we not go back and look at them again? The other thing that's interesting is if I have two tangents from a common external point, so SR and ST are both tangent lines. I know they don't, ST kind of doesn't look so tangent, but it is. So SR and ST are both tangent lines, so SR and ST are tangent segments, with R and T being the points of tangency. Then SR must be congruent to ST. So those two segments have to be congruent. So again, what are we learning? We're learning about right angles. We're learning about things being congruent. What are we going to do? We're going to use that to set up and solve equations. So right here, this question says, is ST tangent to circle P? Well, there's one way to find out. If it's going to be tangent, then this has to be a right angle. Angle STP would have to be a right angle. So the question is that a right angle? The only way to check if that's a right angle is to see if we have a right triangle here. So Pythagorean theorem. We check 12 squared plus 35 squared and compare that to 37 squared. If that's going to be equal, then we have a right triangle. If those two are not equal, then it's not a right triangle. And it's not a right angle, and therefore not a point of tangency. So 12 squared plus 35 squared, and my calculator is 1369, and 37 squared is also 1369. So indeed they are equal, so that is a right angle. So the answer here is yes. Okay, that is a point of tangency, because the converse of Pythagorean theorem tells me that that must be a right triangle, therefore that's a right angle. How nice for us. This is a much more interesting problem. And here's where algebra practice that we did last week is going to come in handy. I want to find the radius of this circle. Now, in order for this to be a tangent line, okay, then this, again, has to be a right angle. So, this has to be a right triangle, so r squared plus 80 squared has to equal this whole side right here squared. But that's going to be r plus 50 squared. Now, just as a reminder from last week, r plus 50 squared does not equal r squared plus 2,500. We have to FOIL that out. Okay? That's r plus 50 times r plus 50. That's what r plus 50 squared means. So then we FOIL. So my first gives me an r squared. My outside gives me a plus 50r. My inside gives me another plus 50r. And my last gives me a plus 2,500. So when I put that all together, that's r squared plus 100r plus 2,500 equals, on this side, r squared plus 6,400. Now the nice thing here, as messy as this looks, is that my r squareds are going to cancel out. So I get 6,400 equals 100r plus 2,500. And these numbers are actually going to work out quite nicely for us. Subtract 2,500 from each side. And that's, what is that, 3,900? Okay, and divide by 100, which is super nice. R equals 39. Okay? And there we go. We found the length of R that works. So you're going to see problems like this. You're going to have to FOIL that out. That's why we practiced this last week, because you're going to see problems like that. This is pretty straightforward. Obviously, R is a RS and RT are both tangents. We're told that here in the instructions. If that's true, then 28 has to equal 3x plus 4. Nothing could be simpler than that. 24 equals 3x. So x is 8. Gotta love problems like that. Very straightforward. They set up exactly the way you think they would, and they solve quickly. Couple more examples real quick. Is DE tangent to angle C? Again, this has to be a right triangle in order for that to be the case. What some people might get confused about here is the 2 here is only indicating this part right here. You're saying, well, how do I know how long the part is? Well, because the radius of the circle is a constant. Okay? So if this is 3 from C to D, then the other green segment here also has to be 3, which means this whole side now is 5. And if you remember your Pythagorean triples, you remember that 3, 4, 5 is a Pythagorean triple, so that is a right triangle. If not, you can do out your Pythagorean theorem, 3 squared plus 4 squared compared to 5 squared. And you can do it that way too, either way you get 25. Let's jump down to number 8. We'll jump back and hit number 7 last because again, that's the trickiest one. This one, x squared and 9, we know they have to be equal. Solving this is, I don't have to factor, this is just extracting roots because I have x squared by itself. So I take the square root of both sides, and I get x equals plus or minus 3. Obviously, though, one of those answers does not make any sense because I can't have negative length. Well, actually, x could be negative 3, now that I think about it. It's not the length, that's just the value of x. So actually, yeah, we can't have both, okay? So remember that when I take square roots like that, I do get the plus or minus 3. Negative 3 would work for a value for x here because negative 3 squared is 9. We still get a positive length even though the value of x is negative. Finally, this last one sets up like the other example we have. Again, we're going to set up our Pythagorean theorem here for that to be a right angle. So r squared plus 24 squared equals, and we have to do the whole thing, r plus 18 squared. So r squared plus 24 squared, which I think is 576, but I'm just going to double check. Yep. Equals, when I FOIL this out, that's going to be r squared plus 18 plus r plus 18r is going to be a plus 36r for the outside inside, and then 18 squared is 324. The r squareds very graciously cancel each other out. I subtract 324 from each side, so 576 minus 324 is 252. And then I divide that by 36, and I get r equals 7. So those are the types of problems you're going to run into today with the algebra portion. Yes, we will be using the algebra that we dealt with over the last week. So that's our lesson. You could dive into your assignment on big ideas, or if I've created a different assignment, you can do that, but I think it's on big ideas for today. And we'll see you in class tomorrow.